2017 and 2018, we found something that we have never seen before. We found an app store. But it wasn't a regular app store. It was an app store for industrial robots. We downloaded some apps, and one of them caught our attention after we started reverse engineering them, because it implemented a web server. Yes, a web server running on an industrial robot. So we installed it. We installed it on a software that allows to create a simulation of a factory floor, essentially a dynamic digital twin of the factory floor within a virtual machine. So we installed it, and we had our robot with a web server running on it. And this is what we saw when we opened the web page, the main web page, with a browser. There was some robot status here at the bottom, some file system statistics, and the possibility to explore the file system. We could see what files were on the file system, etc. So we spent some time looking at the code. As you can see, the code is not regular language that we see every day. We'll dig more into this. It's just a programming language for ABB robots. Anyhow, what we found out after a while was an unsanitized code path. As you can see here, there is a string concatenation, and if we look carefully, this string is controlled by an attacker, so an external attacker on the network. So we had a classic path traversal vulnerability or path manipulation vulnerability that is usually found in web applications. So we said, well, an attacker on the network with a web application could probably exfiltrate some files. So let's try to exploit it and see if we can actually verify the exploitability. So after we had it running, we placed a file, as you can see it here on the screen, called secrets.txt outside the root directory of the web server. And everything was running on the robot controller, which is the computer that runs the robot. And with a crafted web request, as you can see here, we traversed a couple of levels back in the directory structure, and we were able to exfiltrate the content of the file. And in this case, there was some string. So here's the list of files, for example, and here with the content of the secret file. So we could essentially explore the file system. An interesting thing that we found in the source code of the web server is a comment left by one of the developers. They were saying, browser will remove the /... from a top level request, so it will be converted by the browser. So we see here that the developer is trusting that the web browser will do the data validation, while we know that this isn't a good practice from a security standpoint, because they are essentially assuming that the attacker will never be on the network, and that the attacker will never be able to craft custom HTTP requests, and that the attacker doesn't have the tools to craft custom HTTP requests. So they are essentially unaware of what an attacker could do. Of course, we reported this vulnerability to ABB, which decided to remove the vulnerable web application from the store. When the removal happened, there were a few hundreds downloads of that application, and we also found the application to be distributed on side channels using forum data sharing platforms and things like that. So we don't know whether that app is used somewhere. And when Bloomberg covered our research, a spokesman from ABB said that in addition to these vulnerabilities, they have fixed the issues that we have found, which helped them provide better security for the equipment in the market. The story that you just heard motivated us to dig deeper into this space. So my colleague and I spent about half a year working on this. My name is Federico Maggi. I'm a researcher with Trend Micro. And if you're curious to know how this story continues and concludes, let's keep watching. So there are a series of observations and questions that come from this story. First of all, we learned that the development and delivery of industrial software is changing as well, is under change. Also, we learned that programming languages for industrial automation are different from what we are used to see, for example, in C, Python, Go, or the more mainstream languages. Then we discovered that this is maybe an overlooked issue, because looking at the comment that that developer left on the web server, it really shows that developers do not consider the possibility of having an active attacker on the network. And overall, another question is there other vulnerabilities that can happen in the automation software that is running on top of the regular software stack on industrial machines? So let's try to go through these questions and observations, not necessarily in this order, and let's see what the answers are. Let's start from the beginning. Changing software development and delivery lifecycle. Well, the software development lifecycle in this space is actually very complex. It usually starts with an OEM that supplies the parts, so the robot and the computer that runs the robot, which is usually called robot controller. Then there is a system integrator that designs the automation line, designs the software, designs the workflow, and so on. And they usually rely on a series of external or internal consultants that write specialized software. And then there is a developer that we normally don't see. It's called a third party. We call it the third party developer, that to indicate that they develop integration software or custom libraries that are reused in the final automation software, and so on. And finally, there are the employees, which are those that operate the manufacturing plant. And according to some interviews that we have conducted, they also implement and they develop software as well. So we can see immediately that the complexity of the software supply chain, the software development lifecycle, is quite high. So this means increased opportunity for the attackers. Imagine how many opportunities an attacker has along such a complex development workflow. On the other hand, the fact that we found app stores, the fact that we found libraries, reusable libraries, indicates that the software development lifecycle is becoming more streamlined and probably faster than it used to be in the past, which in turn means less control over the software. On the other hand, if we look at it from a positive point of view, the fact that there are app stores, even though they are not as advanced as common as mobile app stores, the fact that there are app stores is an interesting fact, because within an app store we can implement centralized security policies. We can check every application that is submitted. We can implement code signing, having a proper PKI, and in general we can have more control over the software that ultimately will be running on the robots. So I hope that this model will be actually used in the future to deliver industrial software too, because as of now, there isn't enough control. Okay, secondly, let's focus a little bit on these proprietary and legacy programming languages. Consider that these languages have been designed decades ago and are still used right now in production because there's no easy way to switch from a platform to another. Every vendor has their own dialect, their own language, their own platform. There are some features in common, but the grammar of the language is rather simple. It kind of reminds me of Algol or basic languages, if you're familiar with. But the important point is that there isn't a cross-platform solution. I mean, there are systems that try to integrate and translate across languages, but natively, a program to automate ABB robots will never be able to run on a KUKA or on a Comau robots. They're all different, both from a programming point of view as well as from a runtime point of view. Operating systems are different. There's nothing in common between these technologies. They're all different. We'll closely look at 8 programming languages, and namely ABB, KUKA, Mitsubishi, Kawasaki, Comau, Denso, Universal Robots, and Fanuc. We look at the specifications and technical documents that we could find online. These languages are almost exclusively focused on automation. As you can see here, there's a simple example of an ABB program written to move the robotic arm from point 0, point A, to point B. Here you see the definition of the targets, the coordinates in the 3D space. And then we have a for loop that move the joints, then wait, then move the other joint, and then wait in a loop, right? So 10 times back and forth. Most of them also offer something that doesn't have anything to do with automation. All of them, almost all of them, implement file handling routines. They allow to read and write files, essentially. It's a legitimate use case because you maybe need to read data from a file to, I don't know, calculate the coordinates. So maybe you need some parameters that describe the physics of the components that you are handling with your robotic arm, or maybe you simply need to write a log file, a journal of all of the operations that the robot performs for auditing purposes. Probably the most surprising finding was to discover that almost all of the languages allow what I call function pointers and dynamic memory. So if you're familiar with C programming or in general programming, dynamic programming, you know that if you have the possibility to load code at runtime, you can develop very powerful programs that change at runtime. And that's exactly what this functionalities is about. Most of these languages allow to retrieve code that is only available at runtime. So for example, from a network, from a file or whatever, load it into the memory and then jump there. So this means that you can have a program that changes its behavior at runtime. Every time you load it is different. And if you are a vulnerability researcher, you know that this is a very powerful primitive because it gives you read and write access to the memory. You can change the control flow essentially. And all of the languages allow communication. So even if these languages are proprietary, there is the possibility to integrate them with external systems by developing custom integrations. At the runtime level, there isn't the notion of privilege separation like we have in modern operating systems, such as mobile operating systems. There's something like 30 years of innovation between the two designs. And the difference is that on a robotic operating system in general, the OS and the hardware resources are considered as a flat space with no separation, no mediated access. So the user programs can access the entire system. As long as you can run a program, there's no restriction on what you can do. I mean, there is very limited restrictions. Whereas in modern operating systems, such as on a mobile phone, you can restrict an app from accessing the camera, accessing the internet, or accessing the files, and so on. So you have a very granular permission system. On the other hand, on a robotic operating system, you can only have role-based access control on a user level, in the sense that you can tell, okay, that user is able to run a program or not. But once the program is running, that program has full access to the system. Which brings me to thinking that maybe there is a lack of awareness in this space. Maybe these issues are overlooked because they are there, right? We have the technical facts that tell us that all of these issues are there. So we say, well, maybe they're not used, right? We asked about 20 automation engineers, and if you consider all of the answers, all of them told us that in one way or another, they use the functionalities that we consider as dangerous. So network sockets, file operations, dynamic code loading are used by most of the people that we talk to. Maybe our sample is biased, yes. So let's expand a little bit more. It seems that automation engineers do not really talk a lot about cybersecurity. The numbers that you see there on the right-hand side of the slide are the estimates of the number of conversations about cybersecurity. And these conversations are taken from the online communities, the main online communities, the most active online communities, some of them being on the internet before 2000, where automation engineers used to talk to their peers. They go there and discuss. So forums, essentially, very highly specialized forums. And if we extract the conversations that contain security-related terms, such as security, exploit, or hack, or vulnerability. I mean, these terminologies that is normally indicating that a conversation is about cybersecurity. We found only very few conversations. In some cases, not even a single conversation about cybersecurity. So, as you can see, very low. Another question is are there other classes of vulnerability other than the path traversal that we have seen in our story? In general, the combination of security sensitive features of the language, of the platform, or whatever you're using as a target, and the lack of input validation means that there is a potential vulnerability. And this is because the language has some features that allow you privileged access to the system. And on the other hand, with the lack of input validation, you let the attackers control your data flow. So the combination of the two creates the venue for a vulnerability. We cannot control the presence of security sensitive features because we cannot change the technology fast. But we can actually act on the lack of input validation. And that's the whole point about awareness in this space. And looking at about 100 files that we found on public repositories, which may not be as representative as a production code, because we don't have access to production code. If you have, please contact me. We found that most of them contain vulnerabilities. We found at least one path traversal that we reported. We found unrestricted movement commands, which means that the attacker exploiting such a vulnerability will be able to control the robot. And then we found another case which is very close to remote code execution. We call it unrestricted function calls. So let's go one after the other. So path traversal we've already looked at. Let's talk about unrestricted movement commands. The notion of motion server you can think of it as a network service that is sitting in front of the robot and allows external programs to talk to the robot in a sort of a common language. So this is the most frequent case where we found unrestricted movement commands vulnerability. A motion server takes a stream of coordinates, in this case degree 20 is an example, and gives these coordinates to the functions that perform the movements. So we can skip for a moment on the fact that there is no input validation. Sorry, there is no authentication because maybe this machine is a firewall, so there are other functionality. But let's see what happens if there is no input validation. Just allow me to open a parenthesis. The ROS project, which stands for Robotic Operating System, the industrial version in particular, uses motion servers to allow external software to talk to the robots. So it's probably the system, it's an open source project, and it's probably the system that makes that uses motion servers the most, because it allows to interoperate between different technologies. So there is one motion server for KUKA, one motion server for ABB, one motion server for Comau, and they have several drivers. And the fact that it's open source allowed us to scrutinize the code and look for vulnerabilities. So without input validation, if an attacker on the network sends unexpected data, what can happen is that they can cause interruption in the movements, or maybe they can even control where the robot is moving to a certain degree. For sure, they can cause something unintended or unexpected. We have verified this in a lab on a robot. Yes, there are multiple layers of validation. So the program is not the only place where validation can happen. That's why it is very important to have a safety system in place, because a safety system can act directly on the motors and block the motors, for example, if they are going to move the robot outside the allowed coordinates. We verified what happened in a lab if the safety system is not configured correctly. And what happened is that we were able to damage the hand of the robot because of a lack of validation. Instead, with input validation, you can at least block unintended coordinates or unintended data from being interpreted by the program. So you even take some burden off the program. Here's an example motion server. It uses the Ethernet KUKA interface, hardware interface, which is essentially a socket, a network socket, to receive coordinates, 6 points, and then it passes these 6 points, which are essentially an array of real numbers, to the PTP program, which stands for point to point. The PTP function, tells the robot to go from a certain point to another point. So the trajectory is calculated automatically. After disclosing our findings to the ROS Industrial Consortium, they released a very practical, very useful guide that tells you how to mitigate this issue, since they couldn't remove the vulnerability in their the current version of ROS. They suggest you how to configure the network to prevent the exploitation of this vulnerability. We'll get back to this in a while. There is also an SES cert alert about our findings, so if you're interested in the details, you can check it out. Another interesting vulnerability class that we found is when the robot executes a function which name is determined at runtime or from data that the attacker can influence. For example, in this program here that used to be on a public repository, now has been removed. But fortunately, it's only a demonstration program, an educational program. we found that it was possible. I mean, the program allowed to receive some data from the network, from a socket, as you can see here. Then from that data, calculate a string, extract a string, and then under certain conditions, the percent instruction tells the robot to execute the function, which name is determined by this string. So an attacker will be able to send any function name and just call that function name at runtime because there's no restrictions. Yes, this is just quote unquote an educational program, but if it's used to teach others how to code, then I don't think this is a very instructional or security aware educational code. Clearly, there should be a limited set of functions that we allow the robot to run, right? We should have a checklist, and if it's outside the ranges, so to speak, of allowed functions, we don't execute it. The more functions the more freedom we give to the attacker, the closer we get to a remote code execution, because ultimately, if we let the attacker call an arbitrary function, and if we let the attacker influence the arguments of that function, we have something very close to RCE. Is there anything beyond vulnerabilities? Is there anything else that can happen that a threat actor can leverage? Well, the question is, are these languages powerful enough to write malware? Let's see. What do we need to write malware? We need to be able to load or send data from the network. We need to scan network for targets if we want to propagate, and we need to jump to code available at runtime. All of these three functionalities are there. We have seen them in the table before. And then last, we need the language to be Turing complete. And all of these languages are Turing complete because they have conditional statements and loop statements. So we have all of the ingredients. So we tried to see if we could develop a generic malware dropper, and we ended up implementing one. Here is a program that reads data from the network, then writes such data onto a file, and then using their dynamic code loading capability, load that file and call the main routine of that file. So it is possible to run dynamic code at runtime, which means having a malware dropper. Can we scan the network? Yes, we develop a simple network scanner on a limited range of ports, but you can just customize this. Can we exfiltrate files? Yes, we can navigate a tree of directories, and we can send the content or the list of files over a socket or over another exfiltration mechanism. So it is possible to exfiltrate some files. So I think it's time for a little demonstration of a program, a malicious program that we have developed in our lab to demonstrate that it is possible to have self-propagating malware on the factory floor. So now we have a vulnerable program, a more vulnerable robot, which is also already infected. And we also have another two robots which are not infected, but are still running a vulnerable program written in the same control logic language. And here we have the third one. So we have a 3-robot system. And now we have an attacker that uses the first infected robot to scan the rest of the network. The robots on the right are isolated from the rest of the network and are only connected to the first robot, which is also connected as a gateway to the rest of the network. And as you can see, the attacker has found 2 other vulnerable targets, which are robot number 2 and robot number 3 on the right. And now the attacker can invoke the propagation routine, telling the malware on the first robot to find and propagate to other targets. And we can actually run the automation system, the factory floor, just to show you that things can happen even if the robots are running. So now they're performing a very simple pick and place task, just to show you that there is no disruption of the operations, unless of course the attacker would like to have disruption. And here we see that the second controller, which wasn't infected, is infected. And notice that the IP has been retained. And as well, the third one. Great, so let's go back. The question now is, what options does an attacker have to plant such malware in a factory? Well, the first option is the software supply chain, which we have seen it's quite complex. So there are some opportunity, for example, to compromise a system integrator or compromise a library along the chain. It wouldn't be the first time that attackers decide to go indirectly to hit the final target. For example, in 2015, there was the Xcode ghost malware that relied on a modified version of the Xcode development environment to target iOS applications. So instead of distributing an infected iOS app, they hit the target before. And the same is happening in 2020. We already have 3 cases. The Octopus malware scanner found on GitHub to infect NetBeans projects. Once again, another malware discovered by Trend Micro that infected Xcode projects, trying to propagate that way. And recently there was a report by Bitdefender which found that the StrongPD APT group used to use 3D Studio Max plugins to distribute exploits. The second option is that the attacker weaponizes a remote code execution vulnerability. We have seen that even in educational code, we have found something very similar to a remote code execution. We had limited functions that we could execute as an attacker, but if an attacker finds an RCE in a more complex production program, then they can use that for the first infection. And the third option brings back our App Store that we have seen at the beginning of our story. App stores distribute apps that will either run directly on the robot, or in the most common case, they run on the engineering workstation, which is used to produce software that will run on the controller, on the robot controller. So it's one more step. Anyways, there is a chain from the attacker through the App Store to the robot. And the App Stores become a sort of a gatekeeper. They have an important role here if they want to prevent users from downloading infected software. And this is how we are used to perceive, we are used to assume that App Stores do this, at least in the mobile world. This is how they do. Among all of the app stores that we have found, we think that the ABB App Store is the most advanced one because it really implements all of the functionalities of an app store. They have a complete workflow that allows developers to register. The reason why also we focused on ABB in this presentation is because there was a vulnerability that we reported and ABB fixed in their backend that allowed a malicious actor to upload a malicious app, bypass the checking mechanism, the validation mechanism, and distributing that malicious applications to end users. We have verified that if you uploaded a application, even if the application was still pending for approval, as you can see here from the left, it was already immediately available to download with one-click installation right within the engineering software running on the engineering workstation. So anyone could upload a malicious application and have it immediately available to the users. But fortunately, now ABB has fixed the issue. Another thing, we went one step further. Another thing that we wanted to verify is if there was any manual checks, any human in between to check whether the applications were good or not. So we uploaded a completely benign application that was alerting the developers, alerting the human that we we were assuming were in the process, to telling them, hey, this application is just a test application, you shouldn't approve it, you shouldn't use it because it's only here for research purposes. But actually the application went through. So it means that there was a business process that didn't assume that somebody would try to upload something malicious. We found a similar opportunity in the KUKA system, but I don't have time to go through. If you're interested, there is a ICS cert advisory on the KUKA Sim Pro, and this time you have to upgrade to the most recent version if you want the fix. Whereas for ABB, the fix has been applied on the back end as well. Here the issue was a little bit different. Instead of apps, the target was digital twins. So an attacker could upload modified digital twins, and there wasn't a very strong integrity mechanism that would prevent somebody to alter the digital twins. So the software wouldn't recognize if there was any alteration. Okay, so this brings me to wrap up a little bit and see what remediation approaches we can adopt. We want to call the attention of automation engineers, system integrators, and OEMs. And we want to differentiate between existing deployments, so robots that are running right now, robot systems that are going to be deployed in the future, and future deployments we mean next generation robots. Network segmentation is probably the main and the easiest to implement remediation that can be done to prevent exploitation of vulnerabilities that we found and similar. As I said at the beginning, as a result of our disclosure, the ROS Industrial Consortium produced and published a nice guideline that tells you that you shouldn't configure your ROS PC like this, but you should put the ROS PC between the network and the robot, so not on a flat network like this. So there should be a segmentation, right? That's just one of the examples. In our paper that is available at bit.ly/ROG automation, we focus instead of secure coding practices. So we port the main concepts that are well known for IT programmers to develop secure programs. We port them, we adapt them for OT development folks, for OT development audience. So we use different languages, we use different examples, and we walk the reader through the main, what I think are the basics, the most important and fundamental aspects of secure programming, which means input validation, authentication of the input, access control on the requested resources. Only then you can run the actual automation logic. And then you have to apply output sanitization. All of this is well known to IT developers, but I think that at least according to the interviews that we run, and as well as the analysis of the conversations, we have seen that there isn't a lot of awareness in this space. So maybe the way that we should deliver the same message is through different examples, using different cases and different languages. So we provide, in the paper, we provide concrete examples written in the custom programming languages that are used for industrial automation. So hopefully this will help get the message through. To catch vulnerabilities and malicious programs, we develop an automated system that allows you to implement, this is just a prototype, but hopefully in the future will allow to implement completely automated checks to prevent a vulnerable or malicious program to go into production. I don't want to spoil too much because this paper will be, the system will be officially presented in October 5th to 9th at the Asia ACM CCS conference taking place in Taipei. And our collaborator Marcello Pogliani from Politecnico di Milano will be there to give you a demonstration and walk through the entire system internals. As I said, I don't want to spoil too much. I just want to give you a very brief overview of how the system works. We differentiate between sensitive sources and sensitive sinks. So the sensitive sources are given a program, all of the functions that allow you to consume data that could be attacker controlled. So for example, file handling, inbound network, also the UI, if we assume that there can be an insider attacker, the UI of the console used to program or to maneuver the robot and so on. Whereas sensitive sinks are all of those functions that somehow allow access to the resources. So are all of those functions that determine if an attacker can have impact on the system. So for instance, a robot movement is an example of a sensitive sink, because if an attacker can craft a file that specifies how the robot can move, then the attacker has compromised how the process is supposed to work. And similar goes for file handling operation, or most importantly, the call by name functionality, which is the function pointer equivalent in these languages. The system is based on the taint analysis, and we perform taint analysis through control flow graphs. So first we build the abstract syntax tree, then we create the control flow graphs, which we combine together to have a comprehensive control flow of the entire program. And on top of that, we calculate all of the data flows, and given a set of patterns, we see whether those patterns match a list of potentially vulnerable pattern or a list of potentially abused features, so like malware. Right? As an example, I want to show you briefly the output. It's a simple JSON file that tells us that the tool has found a sensitive source that is connected to a sensitive sink. And this is to bring back the first example I gave you of the motion server. So here we have data coming from the network that in another function, in another file, and so on, is used to influence the movements of the robot. So even if it's multi-step, the program can catch these cases. And I can imagine myself having something like this integrated right into the development environment. So they alert the developer that, hey, maybe you should check the source of this data because it's unsanitized. Anyways, I'll leave it up to our collaborator Marcello Pogliani to give you a comprehensive description. So note down Taipei, October 5 to 9, Asia CCS. And last, I think that OEMs can really make a difference in the next generation of industrial automation languages, in the sense that together with system integrators, they can, for example, offer security libraries to implement security checks or to implement strong cryptographic primitives and so on. And they can also have a word on how the next generation of operating system for robots will be designed, because they can implement, for example, privilege separation. They can allow access to resources only if the operator checks if the program is allowed to access those resources. So we can limit all of the cases. And they can also start implementing code signing, which is, I think, the only way to prevent unwanted software to end up being executed on a machine. So to conclude, working on this research for me was like going 25 years back in the past. Do you remember how easy it was to find and exploit vulnerabilities in web applications? I mean, input validation style vulnerabilities were probably the most common vulnerability in web application. Now, it's way more difficult to find them, but hey, we have found a completely new set of languages that have similar vulnerabilities now. Secondly, the most important thing I think you should bring back home is that the lack of resource isolation makes this issue very powerful, because even if it's just an input validation routine, since there is no separation of the privileges, there is no separation, no mediated access to the resources, an attacker may have serious impact. So we ask automation engineers to please try to follow security guidelines, and we ask CISOs to please consider to audit logic written in this proprietary language. So do not exclude languages that are not non-mainstream in your auditing. We have a working prototype that can find vulnerabilities in ABB and KUKA programs. If you're interested in having your program checked, please reach out. You can find my name on the internet. I'm on Twitter as well. And if you're interested in the details, here you find the URLs where you can download our papers. Thank you very much for following.